Hello, my name is Jehan Shalabi. I'm a rising senior at the New Jersey Institute of Technology, majoring in electrical engineering. This summer, I worked with Dr. Jacopo Benfi and Professor Nicholas Roy on efficient ground vehicle navigation using aerial images. I worked in the robust robotics group at the Computer Science and Artificial Intelligence Laboratory at MIT. So the significance of autonomous ground vehicles is that they can be used to explore diverse outdoor environments and novel terrains for many applications such as search and rescue, military surveillance, autonomous package deliveries, agricultural mapping, and inspection. A standard pathfinding approach in robotic navigation is you first build an occupancy map of the environment with local sensors, and then you plan a path, assuming that the unknown space is traversable meaning that there are no dead ends on the path. And then if the unknown space is actually not traversable, you would have to replan the path all over again. And so this is actually difficult because traditional pathfinding approaches in novel environments involves iteratively building a map and replanning as previous unknown parts of the environment are revealed. And this leads to inefficient trajectories such as going down dead ends because they haven't been seen yet. And this is much more time consuming and results in longer distances traveled by the ground vehicle. So the problem we want to solve is how can we extend the ground vehicle sensing range to minimize the time it takes to reach a destination. Our solution uses aerial images acquired by a quadrotor to guide the ground robot's path and find efficient routes that avoid dead ends. And so as the quadrotor hovers at high altitudes, it easily acts as an additional long-range sensor for the ground vehicle. And then aerial images, such as the image in the mid-right of the environment, can be used by the ground robot to determine which regions beyond its sensing range are traversable. And to investigate this possibility, I used a high-fidelity simulator developed by the Army Research Laboratory. The methods I used include world camera transformations, image segmentation, and path planning. The image on the right is an overall summary of my research. So a ROS node is basically the robot operating system node, and it's a piece of software I developed over the summer. And so the inputs to the ROS node includes the quadrotor aerial image and the goal coordinates of the ground vehicle. And then typically the start and goal positions for the ground vehicle are given with respect to some world reference frame. And so we have to get them relative to pixel coordinates in the image. And to do this, I first transformed the world coordinates in the camera frame coordinates by passing through the quadrotor base frame. And then I project those camera frame coordinates, which are still three-dimensional, onto the image. And then this is done again in reverse once the path is computed to retrieve the actual waypoints in world coordinates. So for the image segmentation, you can see the image on the bottom right is a RGB or colored image of from the quadrotor, and the image above it is the segmented image. So I used RGB thresholding to differentiate between objects in the environment. RGB thresholding is basically setting a list of threshold parameters for the red, green, blue pixels in the image. And so anything that is an obstacle, which in this case are the buildings, are covered in white pixels, and anything that is free space is in black pixels. Next, we computed the actual path using the A* search algorithm and make sure that the ground vehicle follows that path. And so you can see the path is covered with orange pixels. This is the path found with A* search algorithm. And then the start position is in red pixels and the goal position is in green pixels. And you can also note how the A* search algorithm computed the shortest distance path from one point to another. So the results of my research include a simulation video of my results. And so this is a world map of the simulation environment, and then the blue dots are the waypoints that are obtained by sparsifying the path obtained on the image. And then these waypoints are tracked by the ground vehicle navigation software. And so you can see how the ground vehicle is actually following those waypoints, and will also follow the orange pixels in the segmented image. So in this particular example, you can see the image on the left. You can see that the ground vehicle took 2 seconds to plan a path on the image, and the A* search algorithm explored 256 nodes. So my future research includes increasing the mapping range by stitching segmented images from multiple quadrotor viewpoints And to do this, we would also have to navigate the quad rotor and not just the ground vehicle. And for emission, we would need multiple goals. And also we wanted to use a more robust segmentation approach by learning a model from real simulated data or actual real world data. So an example includes using neural networks instead of RGB thresholding for object segmentation.